Imagine a massive desert expanse littered with giant stones that mysteriously glide across the ground, leaving winding tracks in their wake. Sounds unbelievable, right? But that's exactly the puzzle that has captivated scientists and adventurers at California's Death Valley for generations. These stones, known as racing rocks or sailing stones, sparked wild theories, from epic storms rolling them to supernatural forces at work. But here's where it gets controversial. The real reason behind their movement is stranger and more fascinating than many ever imagined. Racetrack Playa is famous for these enigmatic rocks, some weighing more than 2 hefty NFL players combined. Their twisted trails seem impossible. The rocks appear far too heavy and awkwardly shaped to be merely shoved along by gusts of wind. Could there be another explanation? In 2014, Professor Richard Norris finally solved the mystery. He witnessed the rocks moving when thin sheets of ice formed beneath them, literally floating the stones and pushing them along. And this is the part most people miss. The conditions needed for this phenomenon are incredibly rare. The ground at Racetrack Playa is so flat that when the valley occasionally experiences heavy winter rains, the water remains pooled on the surface. At night, this water freezes into a solid layer of ice. As the sun rises, the ice sheets begin to float atop a shallow layer of water, acting like sails that catch the wind. With a much larger surface area than the rocks themselves, these floating ice slabs can exert enough force to slowly nudge the boulders across the slippery, saturated earth. As the ice melts and the water drains, it leaves behind an unmistakable trail in the mud, a testament to this fleeting natural phenomenon. Curious to see what else this process could inspire, Virginia Tech PhD student Jack Topachik took the idea indoors and ran his own experiment. Rather than duplicating Death Valley's exact conditions, he placed a disk of ice onto a grooved aluminum plate. As the ice began to melt, it settled atop a thin film of water. Here's where Topachik's clever twist comes in. He didn't use wind or tilt the surface to force movement. Yet, surprisingly, the ice disk still traveled across the plate. Topachik described it vividly. A good analogy is tubing down a river. Except in this case, channels carved into the metal plate direct the flow of water, pushing the ice along without any help from gravity. But the experiment threw up even more surprises. When the team coated their aluminum plate with water-repellent material, expecting the ice to slide faster, they were puzzled to find it stalled at first, then suddenly shot across the plate at an unexpectedly high speed. They dubbed this the slingshot effect. According to Associate Professor Jonathan Barreco, the waterproof surface causes extra meltwater to be pushed out from beneath the disc, making it momentarily stick to the metal's ridges. As the water continues to flow and builds up at the front edge, it creates a tension imbalance that suddenly yanks the disc forward. Now, here's a hot topic to debate. The ice disk's movement is much faster and results from a different mechanism than Death Valley's wandering rocks. In fact, it's more like another phenomenon called the Leidenfrost effect, where water droplets skate across hot metal surfaces, carried by a floating layer of vapor. Yet, while this effect usually requires the liquid to evaporate into gas, Topachik's experiments proved that simple melting from solid to liquid can also propel surprisingly large disks with no need to vaporize. The potential applications are tantalizing and controversial. Barreco suggests that if you shape the surface into a circle, the ice would continuously spin as it melted. Now, imagine adding magnets to the top of the spinning ice disks. Could such motion be harnessed to generate power? Of course, such a system isn't going to cheat nature. The energy you'd need to freeze and refreeze the ice would vastly outweigh the energy produced from its spinning. A sobering reminder that perpetual motion remains impossible, no matter how clever the invention. So what's the practical payoff? The researchers propose using this effect for anti-icing technologies, self-cleaning surfaces, or microfluidic devices that don't require external power sources. The study reporting these findings was published in ACS Applied Materials Interfaces. But here's a question that might stir up debate. Is energy harvesting from melting ice just a scientific curiosity, or could it reshape how we design new technology in the future? Do you think the hype around these self-propelling systems is deserved, or are we just chasing after clever party tricks? Share your thoughts, whether you're excited or skeptical, in the comments below.